Welcome friends. In this session we will perform a heat transfer through a composite cylinder by using ANSYS software, and then we have to calculate intermediate temperature, means T1 and T2, and the thermal distribution of a cylinder. Then we have to this solution, analytical solution, compare with the theoretical calculation. Okay, so let's start. A steel pipe line has a inner diameter 100 mm and outer diameter is a 110 mm. Okay, so there is a thermal conductivity is given is a 50 watt per meter Kelvin, and it's covered with a two layer of a insulation, each 50 mm thick. There is a two insulation 1 and insulation 2. Thermal conductivity of inner and outer insulation is a 0.06 and 0.12 watt per meter Kelvin. Then inside surface temperature, means Ti, is a 250 degrees Celsius and outside is a 50 degrees Celsius. Okay, so calculate temperature T1 and T2. So this cylinder I have to draw by using Axi-symmetric method. So see here, there is theoretical calculation. In that R1, R2, R3 and R4 I have to calculate. So R1 is a 50 mm, R2 is a 55 mm, R3 is a 105 mm because there is a thickness is a add. R4 is a 155 mm. Okay, so let's start. Go to preferences, thermal, okay, preprocessor, element type. So there is a add element, solid element and plain 55. Okay, after that go to option and element behavior, means K3, change Axi-symmetric. Okay, go to metal property and add a thermal conductivity. So thermal conductivity of a steel, there is a 50, and another insulation is add, means insulation 1. So there is a 0.06 thermal conductivity, and insulation layer number 3, there also conductivity is given, so there is a 0.12. Okay, after that go to material and exit. So I have to add a 3 layer, a different thermal conductivity. After that go to modeling and create an area by using rectangle and dimension. So first value is 0.05 and 0.055. Okay, suppose y1 is a 0 and height is a, suppose I have to assume as a 0.2. Then apply. Then another layer is a 0.55, means another rectangle is a 0.55, means 0.055 meter and 105. Okay, so apply. After that we have to add a last rectangle, means 105 to 0.155 and okay. So modeling is done now, but there is a 3 different layer, so we have to stick to each other, means go to operate, booleans and glue area. So go to here and pick all. Okay, so area 1, 2, 3 is add now or stick now. Go to meshing, mesh attribute and pick area, select first area. Okay, and material number is a 1. Okay, here is a material number 1 because there is a thermal conductivity is a 50. So okay, go to size control, manual size, area, pick area, select first area. Okay, and value is a 0.004. Okay, then okay, go to mesh, then area, free area, select this and okay. Okay, so first area is a mesh now. Go to mesh attribute again and pick area. Second, okay, so reset and second one. Okay, and select attribute number 2, means material number 2. Okay, size control, pick area, second number. Okay, and here is a 0.35. Okay, and mesh free, select second area. Okay, so meshing is done now. After that, go to again mesh attribute, pick area, third number area. Okay, and choose the attribute number is a 3. Okay, go to size control, area, pick area, third number area. Okay, value is a 0.035 to 0.25. Then okay, mesh free area, select this. Okay, so meshing is done now, each and every element. Now go to solution, define, apply, and apply thermal boundary conditions, mean thermal constraints. Okay, so constraint is a temperature inside and outside. So on a line, select inside line. Okay, inside means left side. Okay, select temperature, and there is a temperature 250. Okay, then again on line, select outside layer, means right side. Okay, and the temperature value is a 50. Okay, so go to solve, current ls means load step. Okay, and solutions are done now. Close. Go to general post processing, plot result, control plot, nodal solution. Then degree of freedom solution and select temperature. Okay, so this is a temperature distribution. Okay, so this is the only front view. So we have to calculate intermediate temperature, means this one and this one also. So go to path operation, define path. So you have to choose a define by node as well as by location. So I will select a location. Okay, by location. So here is the name is a point. Okay, point 1. Then number of point is a 2 only. Okay, you have to choose a 2, 3, 4 and so on. So I will select only 2 because I will calculate only 2 parameters, means T1 and T2. Okay, so okay, then point number 1 and first location means R2 is a 0.055 and Y is suppose 0. No, there is no problem. Okay, and the second point there is a value 105. Okay, then close. After that, go to plot path. Okay, see here there is a point 1 and 2. Okay, then map onto path, degree of freedom solution and temperature. Okay, then plot path item on a graph, select temperature. Okay, so there is a graph. Okay, so I will choose from first value here. So first value is a 249.972 and second value is 96.374. So total temperature is a 1 is 249 and temperature 2 is a 96. Okay, so the values are given now. We have to calculate by analytically. Okay, then go to plot and element. Okay, and go to plot result, control solution, nodal solution, and okay. So this is only front view. So go to plot control and style, symmetric expansion, 2D Axi-symmetric and full expansion and view isometric. Okay, so this is the cylinder. Okay, so after that you have to this solution calculate by using a theoretically. So see here there is a theoretical calculation. So theoretical calculation we calculate first heat transfer rate, means Q. So there is a total 3 layer, 1 layer, 2 layer and 3 layer. So 3 layers means there is a R1, R2 and R3, means resistance 1, resistance 2 and resistance 3. So there is a thermal resistance, 3 thermal resistance. So we have to calculate a 3 thermal resistance R1, R2 and R3. And this is calculating by using length and thermal conductivity. Okay, so in this theoretically we have assume length is a 1, means unit. Okay, so R1, R2, R3 calculate, then total resistance value we have to calculate. Okay, then you have also calculate a heat transfer rate Q is 89.6 watt, and then we have to calculate temperature. So temperature Ti minus To divided by R. Okay, but here is a relation between Ti to T1 and T1 to T2 and T2 to TO. So we will calculate T1. So put this Ti value and Q value and R1 value into this formula. Then we have to T1 value is 249.97 and T2 value is 96.285. So let's check this value, and means theoretical and analytical values closer now. Okay, so go to again path operation and plot path item on a graph. Okay, so see here there is a value 249.972. Okay, there is a value 249.97 degrees Celsius, and T2 value is 96.285. So here is a value 96.274. So this value is much closer now. Okay, that's it. Thank you.